Hi friends, in this video I will introduce the concept of basis and dimension for students who are majoring in subjects other than mathematics. The prerequisites for this lecture are reduced row echelon form of a matrix, independence test method and simplified span method. So let us move forward. What is a basis? So, given a vector space V, a subset S of V is said to be a basis for this vector space if S is linearly independent and S spans V. That is, V is equals to span of S. Let us explore some examples. First, I take trivial vector space. So, if V is singleton 0, then S is equals to phi is a basis for V. Secondly, if I take V is equals to the set of reals, then S is equals to singleton 1 is a basis for V because it is possible to write any real number R as a scalar multiple of 1. So 1 is a basis for S. Dear friends, a basis is a normal English word which means foundation. So a basis is basically a foundation of a vector space. Let us see the next example. So if I now take V to be R2. So R2 basically is the set XY where X and Y are reals. Let us take my set S to be 1, 0, 0, 1. Then obviously this set S is linearly independent. Also, any XY can be written as X into 1, 0 plus Y into 0, 1. So that means any XY can be written as a linear combination of 1, 0 and 0, 1. So that means S spans R2. So S spans R2. S is linearly independent. So that means S is a basis for R2. Such a basis is called standard basis. Similarly, if I take V to be the set of all 2 cross 2 matrices over reals, that is, matrices of the form X, Y, Z, W, where all of these X, Y, Z and W, they are reals. So if I take S to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, then this becomes a basis for V since it is linearly independent and it spans V. This basis is again called a standard basis for the set of 2 cross 2 matrices. Similarly, if I take V to be R3, the standard basis would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is my standard basis for R3. Note friends that a basis need not be unique. These are only one examples that I have given you. So if I take a look at R2, there may be other bases as well. For example, if I take my set S to be 2, 0, 0, 2, then that will also be a basis for R2. So a basis need not be unique, but you have to note that the number of elements in each of the bases would be the same. So that means even if R2 has many bases, but all of the bases of R2 will contain only 2 elements. Similarly, if I take R3, there may be infinite number of bases of R3, but the number of elements in each of the bases would be 3. So Coming on to dimension now. Now that we know that the number of elements in each of the bases are the same, that is what my dimension is. So if I have a vector space V, then dimension of V is nothing but cardinality of the bases. So if my basis has n number of elements, then the dimension of V would be n. Accordingly, I have two types of vector spaces. One is finite dimensional vector space and the other one is infinite dimensional vector space. So a finite dimensional vector space has a finite basis and an infinite dimensional vector space has an infinite basis. Going back to the examples that we had just done, so if I take V to be R, my basis was singleton 1. So since there was only one element in the basis, so dimension of V is equals to 1. So that means dimension of real numbers is 1. Similarly, when we took V to be R2, my dimension of V was 2 because I had two elements in the basis. When V was R3, so dimension of V was 3. So in general, if V is Rn, then dimension of V is equals to n. When I had taken V to be M2 cross 2, there were 4 matrices that were used to span V. So dimension of V here was 4 since the elements in the bases were 4 in number. Similarly, if I take the set of polynomials, so if I take Pn, so these are all polynomials of degree less than equal to n. So the basis here would be 1x, x square, xn. So there are n plus 1 elements that are required to write any element of Pn and all of these are linearly independent. So that means S is a basis for Pn. And again, this basis is called the standard basis since there are n plus 1 elements. So that means dimension of Pn is n plus 1. So all of these examples were cases when dimension was finite. So now if I take my set to be P, so set of all polynomials, I am not putting any restriction on the degree of the polynomial. Okay, so now my basis S would be 1, x, x square and so on. It would not end. Now because S is infinite, so P is infinite dimensional. I hope it is clear to you all. So let us now move on to some examples so that it is even clearer. Now in this example we have to show that the set B, which is given by 1 to 1, 2, 3, 1, minus 1, 2, minus 3 is a basis for R3. Now B will be a basis if it is linearly independent and secondly it spans R3. So now what we do is, to find out whether B is linearly independent, we apply ITM. So for ITM, we construct a matrix A whose columns are these vectors. So this is to find out whether B is linearly independent or not. So my matrix A is 1, 2, 1, 2, 3, 1, minus 1, 2, minus 3. After constructing this matrix A, we find the reduced row echelon form of this matrix, and the reduced row echelon form of this matrix here is coming out to be 1, 0, 0, 0, 1, 0, 0, 0, 1. So the RREF of A is coming out to be this. I have written it directly. You can verify it. So now that we see that the RREF is coming out to be this, that means there is a pivot in every column. So that means B is linearly independent. After this step, now I need to show that B spans R3. So for that, what we'll do is we'll take an arbitrary element ABC in R3 and we have to see that whether this element can be written as a linear combination of these elements or not. That is, whether this element ABC can be written as C1U1 plus C2U2 plus C3U3, where U1, U2, U3 are these three vectors. So for this we see whether this system is consistent for all the values of ABC or not. And for that, what do? we write the augmented matrix of this system, and the augmented matrix is, now the augmented matrix would be 1 2 1 2 3 1 minus 1 2 minus 3 and A B C. Okay, so already we have seen above that the RREF of this is coming out to be 1 0 0 0 1 0 0 0 1 of this matrix, and then of course we'll have some elements A, B and C here. So you'll have to redo the entire steps to get the RREF of this. So it is advisable to do this first and then do this. So anyway, now here that I have this as my RREF, it can be seen that this RREF shows that the augmented matrix is always consistent no matter what the values of A, B and C are. Since I do not have any row of the form 0 0 0 0 and then I have C. Since I do not have any row of this form, so my system is always consistent for whatever values of A, B and C. So that means that B spans R3. Now because B is linearly independent, B spans R3, that means that B is a basis for R3. I hope it is clear to you all. If there is any difficulty, please feel free to comment below. Let us move further. Let us move on to maximal linearly independent sets. So maximal linearly independent sets, basically, you know, if I am given a set S of a vector space V. Now S may have any number of vectors, which and you know, I am assuming that V is basically span of S. So I am given that S is spanning V, and I want to find out what is, because S may have any number of vectors, S may have redundant vectors also. By redundant vectors I mean useless vectors also. By useless vectors I mean the vectors that are not contributing to the span. So to find out those vectors which are not redundant vectors, we find out the vectors which are linearly independent in S. So we apply ITM, and when we apply ITM, we get pivot columns. After getting pivot columns, we observe that these columns, you know, they were corresponding to some vectors of S, and the vectors that are corresponding to these pivot columns are actually linearly independent. For example, if I take, suppose this is just a hypothetical example. Suppose if I am writing down the RREF directly. So if I have 0 1 0 and then I have 0 0 0 and 2 3 and here 0 1 0 and 4, sorry, 0 0, and I have something like this. Suppose this is the RREF of some system. Okay, so this is the RREF that I am getting. Now I am assuming that S initially had V1, V2, V3, V4, V5. There were 5 elements in S. I wrote matrix A as V1, V2, V3, V4 and V5. After finding the RREF, I got this. Now here I can see that first, second and fifth columns are pivot columns. So accordingly, my vectors V1, V2, V5 are linearly independent. So basically if I take these into set, so V1, V2, V5, then B is my maximal linearly independent subset of S, and this B will also be a basis for V. because it is already given that V is spanned by S, and I've just removed the redundant vectors from S, and then I get B. So B will also span V, and B is linearly independent. So B is a basis for V. So every maximal linearly independent set is a basis. This is what I mean to say. So let us take an example. Now I have taken set S that contains 1, 2, 3, 4, 5 number of elements, and I need to find a subset of S that forms a basis for V. So that means I need to find my maximal linearly independent subset of S. This is what I have to do. So now what I do is, because I need to find the maximum linearly independent subset of S, I apply ITM. So I construct matrix A, which is 1, minus 2, 1, 3, 1, minus 2, 5, minus 3, 0, 5, 4, minus 5, 0, 0, 0. After constructing this matrix A, we find the RREF. Again, I am writing it directly, but you can verify that you are getting this as the RREF. So 1, 0, 0, 0, 1, 0, 2, 1, 0, minus 1, 2, 0, 0, 0, 0. So I am getting this to be my RREF. Now from RREF, I can see that there are only two pivot columns, which is first and second. So that means vectors corresponding to these, that means my vector v1 and vector v2 will constitute B. So that means B is equals to 1, minus 2, 1, 3, 1, minus 2. So this is my maximal linearly independent subset of S. So B is my basis. Note that it is given that V is equals to span S. This is a condition that is required because I am not proving that B is spanning V. So if this is not given, then I'll have to show that B spans V. So since it is given that V is spanning S and I am only removing the redundant vectors, so B, which is my maximal linearly independent subset of S, will come out to be the basis for V. Next, we move on to define minimal spanning set. Now, what is a minimal spanning set? Given a vector space V, if I have a set B which contains the minimum number of vectors that are required to span V. So if B contains V1, V2, Vn, then these are the minimum number of vectors that are required to span V. Then B is said to be a basis for V. So that means minimal spanning set is always a basis. Now, if I am given some question where I am given a vector space V and I am given a set S that contains some vectors, suppose U1, U2, Un, and I am asked to find out, and it is also given that V is equals to span S, and I have to find a basis for S, then there are two ways we can do it. First, we have already discussed, we can either find out the maximal linearly independent subset of S and we will get that to be the basis, or what we can do is, using these vectors of S, we can find the minimal spanning set. Now to find out the minimal spanning set, we apply SSM, that is simplified span method. So what we do is, we construct a matrix A whose rows are vectors of S. So this is my first row, this is my second row and my nth row. After constructing the matrix A, we find the RREF. And in the RREF, the non-zero rows, would be the vectors that would constitute my minimal spanning set. And that will be a basis. I will just explain it through an example so it is a lot clearer. Now again I've considered the same example. So I've taken S to be this, but here the question is different. There the question was find a subset of S that was a basis for this. Now here I am not asked to find a subset, because if I applied simplified span method, my simplified span will not be a subset of S. So here it is written find a basis for V is equals to span S. Now it is your choice whether you want to find a subset of S or you want to find out any basis. So if you want to find out a subset of S, then again you have to do it as previously. You have to apply independence test method and you need to get your maximal linearly independent subset of S, and that will be a basis. Now here I am applying SSM. So I write down these vectors as rows. So I write these as 1, minus 2, 1, 3, 1, minus 2, 5, minus 3, 0, 5, 4, minus 5, 0, 0, 0. After writing these vectors as rows, we again find the RREF. So RREF here is coming out to be 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, minus 3 by 7, minus 5 by 7, 0, 0, 0. So I have only two non-zero rows, which are these two. So my basis B would be 1, 0, minus 3 by 7, 0, 1, minus 5 by 7. So this is my required basis for V is equals to span S. So here I have applied simplified span method to get my minimal spanning set, and my minimal spanning set would be a basis for V. In the earlier method I had applied ITM to get maximal linearly independent subset of this set S, which was again a basis for V. In both the cases it was given that V is equals to span S. And we can also see that the number of elements in both of the bases are the same. So the dimension of V is 2. So I just repeat it once again. Both maximal linearly independent set and minimal spanning set form a basis for V is equals to span S. If in the question it is asked to find a subset of S, then apply ITM, else you can apply any of the two methods to get the basis. I hope this is clear to all of you. If there is any problem anywhere in the lecture, please feel free to comment.